eigenvectors, and eigen means own. And historically, these actually arose in the area of differential equations, although we typically study them as part of linear algebra. So let's start out by assuming A is an n by n matrix, so it's a square matrix. We ask the following question about A. Are there non-zero vectors for which A times V is a scalar multiple of V? Although we pose this question in the spirit of pure curiosity, there are many situations in scientific computation in which this question arises. The answer to our question, are there non-zero vectors V for which AV is a scalar multiple of V, is yes. And it's a bit of a qualified yes. We need to be willing to consider complex scalars as well as vectors with complex components to make that happen. With the broadening of our viewpoint, we have these vectors. And let's start by looking at some examples. So example 1, we let A be 3, 2, and 7 minus 2, a 2 by 2 matrix. So that's a square matrix. And we want to find a non-zero vector V for which AV is a multiple of V. Now we do a little bit of math, and we can actually find two of these. We didn't really reveal how we got the answer, but A times 1, 1 is 5, 5, which is 5 times 1, 1. And A times 2 minus 7 is minus 8, 28, which is minus 4 times 2 minus 7. So they're multiples of those vectors. For now, you can just assume that some magic happened, like this cool PowerPoint presentation, but by the end of the presentation, you'll be able to do this. Since that didn't involve too much computation, let's move on to another example. So here we let A equal 1, 1 minus 2, 3, and find a non-zero vector V for which AV is a multiple of V. Again, we can find two of these, but the answers involve complex numbers, even though the matrix doesn't contain any complex entries. So it's kind of interesting that we end up with vectors that involve complex numbers multiplied by complex numbers, even though, our original matrix was all real numbers and, in fact, all integers. So, this can actually happen. So this goes to the idea of eigenvalues and eigenvectors. When the equation AX is equal to X is valid and X is not 0, we say that lambda is an eigenvalue of A and X is an accompanying eigenvector. So in example 1, the matrix has 5 as an eigenvalue with eigenvector 1, 1 transposed. 4 is another eigenvalue with accompanying eigenvector 2 minus 7 transposed. Example 2 has complex eigenvalues and eigenvectors. Now, notice A times 0 equal lambda times 0 and A0 is equal to 0 times X. These don't say anything useful about eigenvalues and eigenvectors of A. So a lot of problems in science lead to eigenvalue problems in which the principal question usually is what are the eigenvalues of a given matrix and what are the accompanying eigenvectors. An outstanding application of this theory is to systems of linear differential equations. So let's turn our attention to the eigenspace. And if AX is equal to lambda x and x is not equal to 0, then every non-zero multiple of x is an eigenvector with the same eigenvalue. So if lambda is an eigenvalue of an n by n matrix A, then the set X is equal to AX, or the set X such that AX is equal to lambda X is a subspace of R raised to the n called the eigenspace. It's necessarily of dimension 1. So let's go back to eigenvalues and eigenvectors. And we want to know how to find these eigenvalues. So first of all, we need to have a square matrix A. And we begin by observing that the equation AX is equal to X is equivalent to A minus lambda sub I times X is equal to 0. Since we're interested in non-zero solutions, the matrix A minus lambda I must be singular, that is non-invertible, and therefore determine that A minus lambda I is equal to 0. To find the eigenvalues of this matrix, we find the zeros of the polynomial P given by P of lambda is equal to determinant A minus lambda I. It turns out that P is a polynomial degree n and will have n zeros, provided that we allow complex zeros and count each zero a number of times equal to its multiplicity. Even if the matrix A is real, we need to be prepared for complex eigenvalues, as we saw earlier. The polynomial just described is called the characteristic polynomial of the matrix A. If this polynomial has a repeated factor, such as lambda minus 3 raised to the k, we say that 3 is the root of multiplicity k. Such roots are still eigenvalues, but they can be troublesome when k is greater than 1. Let's take a look at an example. So here we have a matrix 3, 7, 2, minus 2, and P of lambda is the determinant of A minus lambda I, and we find the zeros of that. So first of all, we calculate the determinant, which is 3 minus lambda times minus 2 minus lambda minus 7 times 2 minus 14. That gives us lambda squared minus lambda minus 20. That one we can factor lambda minus 5 and lambda plus 4, so our eigenvalues end up being 5 minus 4. This is a mathematical process from the definition. For small values of n, such as the one that we did here, it works pretty well. And it's called the direct method for computing eigenvalues. In general, an n by n matrix will have a characteristic polynomial of degree n, and its roots are the eigenvalues of A. So these 2 by 2 ones are pretty trivial since we've done factoring since high school. Since the calculation of zeros of a polynomial is numerically challenging, if not unstable, this straightforward procedure is not really recommended for larger matrices. The eigenvalue eigenvector problem is also nonlinear because you have to deal with both lambda and x, which are unknown. In real life, we make use of special software libraries or specialized software for this. Mathematical software systems have single commands to produce a list of eigenvalues computed in the best possible way, which is usually not to determine the characteristic polynomial and subsequently compute its zeros according to the definition. In mathematical software, we can use a single command to compute all the eigenvalues directly, or request the calculation of all eigenvalues and eigenvectors at once. The MATLAB command vd equal eiga produces two arrays, v and d. The array v has eigenvectors of A as its column, and the array d contains all the eigenvalues on its diagonal. So here's what the command looks like. Now, when you put this in, MATLAB responds instantly with the eigenvectors in the array V and the eigenvalues in the diagonal array D. The real eigenvalue is 0.0214, and the complex pair of eigenvalues are 3.9893 plus or minus 5.5601 times I. And behind the scenes, much more complicated computing is taking place. The general procedure has these components. First, by means of similarity transformation, you put A into lower Hessenberg form. This means that all of the elements below the first subdiagonal are 0. Now similar transforms ensure that the eigenvalues are not disturbed. If A is real, further similarity transformations put A into a near diagonal form in which each diagonal element is either a single real number or a 2 by 2 real matrix whose eigenvalues are a pair of conjugate complex numbers. Creating additional zeros just below the diagonal requires some iterative processing because, after all, we are in effect computing the zeros of a polynomial. That being said, let's take a look at some theorems. And Theorem 1 summarizes the special properties of a matrix that impinge on the computing of its eigenvalues. So this tells you what type of eigenvalues you will get for different types of matrices. Theorem 2 says two matrices are similar to one another if there exists a non-singular matrix P such that B is equal to P times A times P inverse. So Theorem 2 states that similar matrices have the same eigenvalues and suggests a strategy for finding eigenvalues of A. We transform the matrix A to a matrix B using a similarity transform. B is equal to P times A times P inverse, in which B has a special structure, and then find the eigenvalues of matrix B. Specifically, if B is triangular or diagonal, the eigenvalues of B are simply the diagonal elements of B. Now we'll talk about Surest Theorem. This states that every square matrix is unitarily similar to a triangular matrix, and the corollaries here are kind of important. Every square real matrix is similar to a triangular matrix, and every square Hermitian matrix is unitarily similar to a diagonal matrix. We can accomplish Surest Theorem by the conjugate transpose of the matrix, but the corollaries here are more important. They allow for transforms which allow us to more easily find eigenvalues and eigenvectors. There's an example on page 385 of the text if you're interested in seeing how this works. Most numerical methods for finding eigenvalues of an n by n matrix A proceed by determining such similarity transforms. Then one eigenvalue at a time is computed, and the deflation process is used to produce an n by n by one matrix A tilde, whose eigenvalues are the same as those of A except for lambda. Any such procedure can be repeated with the matrix A tilde to find as many eigenvalues of the matrix A as desired. In practice, this strategy must be used cautiously because successive eigenvalues can be infected with a round-off error as a problem that's peculiar to numerical analysis. Okay, related idea is Gershgorin's theorem in DIS, and sometimes it's worthwhile to just get a coarse estimate of the eigenvalues and eigenvectors. Gershgorin's theorem in DIS can help us do that, but it's a pretty cool trick regardless that works with complex numbers. So here are some theorems and corollaries, and without reading all of it out loud, we can summarize by saying that this is a whole bunch of complex math involving at least linear algebra, complex numbers, and a bit of geometry. It looks and likely sounds intimidating if we were to read it out loud, but let's see it work. I think it makes a little more sense if we work it out. So consider the matrix given here. A is equal to 4 minus I, 2I, minus 1, 2I, 2, 1 minus 1 minus 5. Now, this matrix looks intimidating. We've got complex values here, but we can use the theorems and corollaries to find the Gershgorin DIS. We just need to be aware of how to compute magnitudes in complex numbers, which is basically the Euclidean distance from the complex number to the origin in the complex plane. So it's just a Euclidean distance calculation. So we use the rows to find three of the DIS. So we start out with the first row, 4 minus I, 2, and I. The center is at the element that is on the diagonal of the matrix A, which is 4 minus I, and the radius is the magnitude of the other two elements added together. So the magnitude of 2 is 2 squared square root 2, and 1 squared square root, which is 1. 2 plus 1 is 3. So the center of this disk is at 4 minus I with radius 3. Disk 2, the center is at 2I, which is the element on the diagonal, and the distance is minus 1 squared plus 2 squared. Square root is 3. And last but not least, disk 3 is centered at minus 5, with r is equal to 1 squared plus the square root of minus 1 squared, which is equal to 2. Now we need to deal with the columns to find the other three disks. And using the same process, disk 1 is centered at 4 minus I with radius 2. Disk 2 is centered at 2I with radius 3. And disk 3 is centered at minus 5 with radius 3. Now what we do is we can plot these disks on the imaginary plane. And the imaginary plane has two axes, the real axis and the imaginary axis. And look at the center of the intersection for estimates of the eigenvalues. The exact eigenvalues here are 3.7208 minus 1.05461I, 4.5602 plus minus 0.2849 times I, minus 0.1605 plus 23395I. The dots that are actually in the center of the Gershgorin disk are 4 minus I, 2I, and minus 5. And these are within reasonable proximity. You can see the centers marked by the dots and the stars that are the actual eigenvalues. So, we actually get fairly good results, or a nice approximation using these Gershgorin disks. The other idea discussed in this chapter is singular value decomposition. This requires further knowledge of linear algebra, and particularly the diagonalization of symmetric matrices, eigenvalues, eigenvectors, rank, column space, and norms. All that fun stuff that you learned or will learn in Math 311. The singular value decomposition is a general purpose tool that has many uses, particularly in least squared problems that we're going to look at in Chapter 9. And again, I'll try to make Chapter 9 so that it doesn't deal with too much of that theoretical math. It can be applied to any matrix, a singular value decomposition, whether square or not. And we'll cover the general outline of this procedure because it's actually quite complicated. You can find an example of this on page 390 to 391. And here is the procedure. We find the eigenvalues of A transpose A, find the eigenvectors, Then find the orthonormal set of eigenvectors. Form V is equal to V1, V2 as a matrix. And then form D by placing square roots of the eigenvectors, which are the sigma sub I, on the leading diagonal. Now, these sigma sub I can be used to compute the condition number as well, which gives us a bound on the complexity of the matrix for Gaussian elimination and other procedures. So they are useful as part of this process. We compute U sub I that form U, then use the Gram-Schmidt orthogonalization process, normalize and compute U, and then get the singular value decomposition. Fortunately, there's software to do precisely this, so we don't have to write this from scratch. And in fact, I don't think Cheney and Kincaid have pseudocode in this particular chapter, because it's just best left to the specialized mathematical software like Mathematica and Maple. So as an example, and looking at those systems of differential equations, they can be utilized, eigenvector and eigenvalue analysis can be utilized for a variety of differential equations. Now, I don't know who builds this stuff besides physicists and introductory engineering professors who teach statics and dynamics, but consider a system of two masses and three springs, which are constrained to only move in the horizontal direction. Now, what we can do is we can actually write the equations of the motion in matrix vector form. And you'll notice here that we have a second-order differential equation. By assuming that the solution is purely oscillatory, that's no damping, which means there's no decrease in the amplitude of the oscillation as a result of energy being drained from the system to overcome friction or other resistant forces. We have x is equal to v times e to the I wt. In matrix form, we get x1, x2 is equal to v1, v2 times e to the I wt. By differentiation, we can get another form for x double prime and get minus beta alpha alpha minus beta times x is equal to minus w squared x. This is the eigenvalue problem, ax is equal to lambda x, where lambda is equal to minus w squared, and eigenvalues can be found from its characteristic equation. So we get beta plus or minus alpha. For simplicity, we assume that unit masses and unit springs, so that beta is equal to 2 and alpha is equal to 1, and we get the matrix minus 2, 1, 1, minus 2. The roots of the characteristic equation for this matrix are 3 and 1. For the first eigenvalue, we obtain 0. We obtain 1, 1, 1, 1, v, 1, 1, v1, 2, and v1 is equal to the 1 minus 1 for its eigenvector. For the second eigenvector, we get v is equal to 1, 1. And so the general solution of the equations of motion for the two-mass system is given by this equation for x. Because the solution was for square of the frequency, each frequency is used twice, one positive, one negative. We can then use the initial conditions to solve for the unknown coefficients, assuming we know those initial conditions. Okay, so thanks so much for watching.